sort of pause for a little bit and put things in perspective and try to think about what in the world have we been learning. So let me put the entire trig course in perspective, if I may. I think at the beginning of the class we said that some of the central themes in trig, one of the central themes in trig was this idea that if you make a big angle you get a big side, and if you could dominate that idea you could measure things by just looking at it, kind of like this. This was the first promise for trig. If you have a tree and you want to know how tall is that tree, you don't really need to climb up there and then risk falling. All you do is measure this distance over here. Say you measure something like 20 feet, on the safe ground, and then all you do is look up to the tree, and you should be able to figure out how tall it is. We'll call it h. Maybe you can measure this angle, and I'll just make some stuff up. Suppose this angle is 55 degrees, and let me zoom you in there. That's all it takes. That's amazing. This is one little chapter of, by the way, this is supposed to be a right angle. This is one little chapter of dominating this relationship between angles and sides. A big angle makes a big side. Here we talk about these incredible functions that changed everything. These trig functions that tell you the ratios of the sides. For example, here the tangent of 55 degrees would be the ratio of opposite to adjacent. That's the opposite, this is the adjacent, and then you could maybe multiply both sides by 20. So 20 times tangent of 55 degrees is equal to the h, and then you can maybe plug that in a calculator. I just do it by hand. Whoa. And this is approximately I think 1.428 roughly, and then you got to multiply by 20, so you get that h is approximately 28.563, I think. You have to bear with me. I'm just trying to do this in my head. That was the first chapter of the first promise of trig. The idea that you could just look at something and see how tall it is, and that was nice. You can almost think about this as phase one of our class, being able to solve these right triangles. Keep in mind they have to be right triangles. That was the first part of our course. Then we moved on to pay a little bit more attention to the functions. We could say these are properties. Properties of sine of an angle, of cosine of an angle, tangent of an angle. And these properties included the graphs, the shifting, the stretching, blah blah blah. And lately we've been getting into see, we've done graphs, we've done values at famous angles, we've done it on the calculator. And lately we're getting into identities. That's what we've been working on for the last few lectures, on these identities. And then by the time we get done with all these identities, this would be, I would say, about 80% of our normal trig class. And right now we're sort of in the middle of this. And let me just remind you of what happened last time. Last couple lectures, I think we worked on. First we talked about what identities are. They're equations that are true for all values of x's, for which the phrases are defined, and we worked on some strategies to prove identities. We said that you could always try some of these things. You could always try working on one side or the other until you make them look the same. We talked about tweaking a known identity. Sometimes all you do is just tweak it just a little bit, and that's enough to get you a new identity. Sometimes we looked at the graphs. And every once in a while, none of these things work, and you have to start with something amazingly creative and brilliant. And that's probably one of my favorite ways of proving identities. But it's the hardest because you have to be amazingly creative. More creative than an artist, more creative than a poet, than a writer, more creative than any artist that you can imagine. To come up with these ideas that appear to be inspired by I don't know what. Anyways, that's where we're at. We're proving identities. These are the four methods, and just let me remind you which ones we've proven already. So we've proven these ones. I call these the definition identities. This was probably one of the first homework assignments where we started the identities. You have to be comfortable knowing that Sine is the same thing as the opposite of our hypotenuse. That's straight definition. There's nothing to prove there. Same thing for cosine or tangent. But these other ones maybe have something interesting. Like, you should be comfortable knowing that tangent is the same thing as a sine over cosine, as long as the angle matches. Or cotangent, the same thing, cosine over sine, or etc., etc. And these you can prove by just working on one side. Maybe I'll remind you how to prove one of those, just for fun. Before I do that, let me finish the last picture, the big picture for our class. So the first chapter was solving these right triangles. Second chapter studying these functions. You can almost think about it. The next time we're going to come back and solve triangles, but maybe triangles that are not right triangles, but any old oddball triangle. And then some miscellaneous topics, and that will be our course. For the moment, though, we have to. This is where we're at. We're proving identities. We have to continue proving them, and we have to compile a list of the most famous identities, such as this one. In fact, I should just point out to you now, these are the ones we proved last time, the definition identities, and we also talked about the cofunction identities, the ones where you shift the graph and flip it and you end up with the same thing. I'll talk more about these some more. Even odd ones, Pythagoras identities, we talked about those as well. I think I've proven 4 or 5 of these. Anyways, you could put I think I've placed them in a list here where you got all the famous ones: the definition, the cofunctions, the even odd, the Pythagoras, the strategies, and some other ones. These are huge topics. This is major, so this is what we want to spend the next couple lectures on, is proving every single one of these ideas and owning them. Make sure you understand exactly why they are. You must own all of these, and these are super famous. And also, every one of the exercises, I'll have you prove all the famous ones, and then I'll have you prove some of the non-famous ones, and we'll do that in the lectures as well. Anyways, I wanna before I get onto this side, this is really important. This is where we're headed next. This is where we've been. This is where we're going. I want to review again what we've done so far and make sure everybody's up to par on the stuff that we're supposed to have already done. Okay? So let's review some of the ones we've worked on before. These are all by definition. The first one you don't have to prove because it's true by definition. Almost all of them, there's nothing to prove, but maybe some of these other ones you might want to do some stuff to convince yourself. For example, this one, the secant theta is always the same thing as a cosine flipped. Let's just take a look at that for a second and see why that would be the case. Secant theta is the same thing as a 1 over a cosine theta. The techniques that we have available for that would be one of these, and I think that you can just work on sides separately, and I think that will do it. That strategy involves forgetting about the equal sign and trying to see exactly, are they equal? Why should they be? You have to make logical steps here and logical steps here until you make them look the same. Here's the first logical step. The cosine is defined to be, for every angle theta, it's defined to be the ratio of adjacent over hypotenuse. I'm going to call this theta. That's by definition. It would be adjacent all over hypotenuse. And then using your algebra skills, you know that you can flip that, and so you get that's the same thing as hypotenuse over adjacent. Meanwhile, on the other side, the definition of secant is precisely the ratio of the hypotenuse all over the adjacent. And so you're done. They're both equal to this hypotenuse over adjacent for the same reference triangle. Reference angle for theta here, reference angle for theta there. And then you're done. And then you know that they're equal. Some simple argument like that should be used so that you can prove every single one of these. And then whenever you're done with this, which you should have done already, you can put this one aside and say, hey, I own these ones. I got these ones, no problem, they're easy. And if they're not, then you got to keep practicing them. Okay, so next we got these even and odd functions. And basically, even and odd, right, it really has nothing to do with even and odd. Well, It has something to do, but not in a direct way. They really should be called identities where the functions don't care about positive angles or negative angles, because that's what they are. Take the cosine, for example. That identity says that the cosine of any angle x would be the same thing as the cosine of the negative angle x. In other words, cosine doesn't care if the angle is positive or negative. And the fancy name for that is to say that cosine is an even function. It doesn't care if cosine of 30 degrees would be the same thing as cosine of negative 30 degrees. Cosine of 100 degrees would be the same thing as cosine of negative 100 degrees. And the strategy to prove that would be to probably one easy way to do it would probably be to look at the graph. Look at the graph of each one and see how it goes. So you abandon the idea that they're equal. You think, hey, I don't know if they're equal. Let's look at the graphs. So for this one, this is a famous graph. We can do this one immediately. This goes like this. Starts off at 1, goes down to 1, and it goes back up to down to negative 1, and it goes back up to 1, and the period is 360 degrees. The other one is not like that. It's like that, but x gets replaced with negative x. Now think about that. All the positive x's become negative x's. Positive x's become negative x's, so it gets flipped over the y-axis. If you do that, you would get this graph, and you think, well, they're not the same graph, but actually they are. If you just keep on going with, that's just one period, but if you keep on going forever, you'll notice that in fact they are the same graph. So this is one way, although it's not as rigorous of a proof. I'll concede that. It is a nice proof because it's clean, it's simple. All you do is look at the graphs. So that's good to show that cosine of x is the same thing as cosine of negative x. Later on we'll learn more rigorous ways of tackling that, but that should be a good starting point. Okay. Sine is actually different. Sine does care whether the angle is positive or negative. In fact, sine of a negative angle will turn that into a negative sine of the positive version of the angle. And again, the way to see that would be, one way to see that would be to look at the graphs. This one would be sine positive x's become negative x's. So here's the original graph, and then the positive x's become negative x's. So now it becomes this graph. Okay. On the other hand, if you have y is equal to negative sine x, that's the same thing as saying negative y is equal to sine x. So what that says is that positive y's become negative y's. And so I think this one has had it. Here's the original graph, and then all the positive y's become negative y's. So it's going to be flipped over the y-axis. So if you flip it over the y-axis, there's your graph, and it turns out to be exactly the same graph that you have here. So this, another way to say this is to say that flipping over the y results in the same graph as flipping over the x. And when that happens, another way to say that is that the function does care if the angle is positive or negative. It'll turn it. You could pull out that negative out in front of the function, or another fancy way to say that is to say that the function is an odd function. Okay, and using these ideas, you should be able to prove every one of these on the even odd paragraph. After a few minutes, you should be able to own every one of those. By the way, you really only need to prove these by graphing. These other ones you can graph by using the working on one side and using these two. Maybe I'll do one more. For example, the tangent one. Tangent is an odd one. It does care if the angle is positive or negative. You pull that out. So maybe I'll do that one here, and then we'll go on to the next excellent paragraph. So to see the tangent, here goes. You go tangent of negative x is the same thing as negative tangent x. That's what I want to prove. And of all these methods, I'm going to go with the first one. I'm going to work on the side separately, and I'm going to use the old stuff I know. So working on the side separately means you forget that they're you forget about the fact that they're equal, or you Don't assume that they're equal, and you start working on one side or the other. This one we know means negative sine x all over cosine x. On the other hand, this one we know means sine of negative x all over cosine of negative x. Right? And we just got done explaining that cosine is an even function. It doesn't care if the angle is positive or negative. So I could change that denominator into just cosine x. And then in the numerator, we just got done saying that sine is an odd function, so you could pull this negative out, so that becomes negative sine x. And there you go. You've shown that they're the same, and that proves that tangent is an odd function. Okay, using ideas like this, you should be able to prove the rest of that paragraph. Every single one of them you should own, and never ever forget. It's got to be automatic, just like that. That sine of a negative angle becomes negative sine of a positive version, or said differently, it should be automatic that sine is an odd function. Cosine, it should be automatic that you should really understand that cosine is an even function. It doesn't care if you got positive angles or negative angles. Okay, you should own this little paragraph, and then we'll move on to the next one. Okay, the next paragraph I want to look at or review is this cofunction identities, and this one I've talked about before, but I want to talk about it again. And for example, let's take the first one. Sine of an angle is the same thing as cosine of 90 minus an angle. And first of all, the name, the co and the co. You ever wonder why? Who put the co in cotangent, or who put the co in cosine, or who put the co in cosecant? Somebody went around putting co's everywhere, and you may wonder who put the co's everywhere. Well, this part of the story should explain it. Let me take the first one, and then we'll do it two different ways and see what we can learn from that. The first one says that sine of x is the same thing as cosine of 90 degrees minus x. And this one we have actually proven before. And the way we've proved it before was by looking at the graph. Okay? And I'll just, maybe I can do that real briefly, but I really want to do it in a different way. Okay, let's look at the graph. So this graph is pretty simple. It's just sine. That's the world famous sine graph. Let's abandon the idea that they're equal. Let's check. This one, you would first start with, let me see, I'm going to factor out the, first of all, that the cosine doesn't care if the angles are positive or negative. So I could well, I won't even do that because I want to make sure everybody gets it. So I'll do this. This looks like, if I factor out the coefficient, the -1, it looks like just cosine of x, the -1, and then shift it to the right 90 degrees. So first I'm going to graph cosine of -x, and then once I'm done with that, I'll graph cosine. I'll replace x with x minus 90 degrees, and you know, if you multiply that out, you'll see you'll get exactly the same thing: -x and positive 90 degrees, which is what you're supposed to get. So this graph first, the cosine of -x. This is the cosine graph, the usual one. X gets replaced with -x, so all the positive x's become -x's. That gets flipped this way. Okay? And then once you've got this graph, you have to shift it to the right 90 degrees. So this graph right here has to be shifted to the right 90 degrees. So for example, this point right here has to be shifted 90 degrees, so that point will be right there. This point has to be shifted 90 degrees, so it'll be right there. This point has to be shifted 90 degrees, so it'll be right here. In fact, if you shift the whole thing 90 degrees, you'll get exactly a graph like this. Okay? And that graph right there is exactly the same as the sine graph. So this is one way to see that they are the same. You can look at the graphs, compare the graphs, and they are the same graph. And that's what we did before, actually. I did it in more detail last time. Hopefully this will help you jot your brain down and remember what it was all about. What I want to do now is I want to take a different idea, though. That was the old proof. I want to see it differently today as a review, and I want to see who put the co in cosine. Well, suppose that you've got a triangle here, a right triangle, and suppose that this angle is 10 degrees and this is 90. We know that they have to add up to 180. So we know that the other angle, if this is already 90 degrees, this one's 90 degrees, and this one is 10, the other one has to be whatever you need to make 90, because you need 90 more to get 180. So this one has to be 80 degrees. And these guys right here are called complementary angle. That's who put the co in everything. Complementary. These two have to be complementary angles, and that's exactly who put the co in complementary. Think about this one. Suppose I call this one A, B, and C. Suppose you're standing over here and you're thinking to yourself, all right, I want to know what is sine of 10 degrees. And if you're standing over here and you're looking for sine of 10 degrees, you're thinking, all right, sine of 10 degrees would be the ratio of opposite to hypotenuse, so it would be A over C. Now suppose you go on over here and you stand on this side over here and you say, you know what, from this side I want the cosine of 80 degrees of the complementary angle. Well, what would that be from this point of view? What is cosine? Cosine is adjacent over the hypotenuse. So from this point of view, the adjacent would be A and the hypotenuse would be C. So from this point of view, the cosine of 80 degrees looks like A over C. In fact, they are the same. This is really a long-winded way of saying, hey, if you stand at the complementary corner, if you stand at the other corner, the ratio opposite, what was used to be opposite, is now adjacent. So what used to be the opposite of hypotenuse ratio is now, from this corner over here, the adjacent over hypotenuse. So that's what put the co and the cosine. You're looking at the complementary corner and you get the same ratio as the original ratio. That will happen the same for cotangent, cosecant, for everything else. The co just means you're standing at the complementary corner. And then you start to wonder, well, what are the generalizations of this? That was fine for 10 degrees. What if the original one was, for example, 15 degrees? What would the complementary corner be? The complementary corner would have to be 75 degrees. And so you would say that, well, sine of 15 degrees is the same thing as cosine of 75 degrees. Staying at this corner and doing the ratio is the same thing as staying at the complementary corner and take the complementary function ratio. And of course, the other way around would work as well. Sine of 75 degrees would be the same thing as the cosine of 15 degrees, etc., etc. But the fancy way to say this is that sine of any angle theta would be the same thing as cosine of the complementary angle. Which one is a complementary angle? Well, it would be 90 degrees minus theta. That's how you get this ratio. 90 minus 15 gives you 75. That's how you get that. That, my friends, that's the complete and full co-function story. So now you have two tools to handle every one of these. Okay, first tool is look at the graphs. Second tool is start with something a little more creative, just standing on different corners of the triangle. And using those two ideas, you should be able to prove every single one of these. Okay, you should own these. There's no excuse for not. No, these are super famous. You will need them over and over and over and over again. And even if you don't need them, they're just fun to learn because they're interesting. Okay. All right. So that's this corner. Then we got to move on to the one of the most important. Sorry, that's that paragraph. Now we got to move on to this important paragraph, the Pythagoras identities. Let me pause this. Okay, this one I proved I think I've proved 2 or 3 of these last time. If you want to, you can go back and review those videos. Maybe I will prove one more from this paragraph. Then I'll prove this one. The sine theta is equal to plus or minus the square root of 1 minus cosine square theta. And the way I'm going to prove that is by number 2, tweak a known identity. Using a known identity, I will prove that sine theta is equal to plus or minus square root of 1 minus cosine square theta. Here we go. Talk is cheap. First of all, we know that sine theta squared plus cosine squared theta is equal to 1. This is known. This is proven. So I know that I don't have to erase that equal. I can leave it there. I know that that's equal. And I can play around with both sides now because I know and I'll get equal things. The thing that I'm going to do now is I'm going to move or subtract the cosine square from both sides. And that will leave me with this. Sine square theta is equal to 1 minus a cosine square theta. That's just a little algebra to subtract that. And then I'll use the square root property that tells me how to get the square root of this. Sine theta is equal to plus or minus the square root of 1 minus cosine square theta. That's the square root property from your algebra class. And there you go, just like that. That's why they pay me. This identity is done. Now every one of these is really, really important. You should own these. Make sure you can prove them. That was part of the homework. On the homework you have to prove every one of these, and then you have to prove a whole bunch of non-famous ones that use these to prove them. Of course both are important. These are really, really important because they're famous, and the other ones are really important to help you practice proving identities. Now that about settles it. Here's my famous sheet. That settles it for the entire left. Well, there's only one more there, the Euler's identity, and that one's that's the jewel of mathematics, right there. But you're not ready for that yet. So you have to wait a little bit. We'll talk about this one later. With that exception, everything on the left-hand side is you should own. You should feel really, really comfortable with. And if you don't, you need to practice those things that you're not comfortable with. Let me review the left side for you. The definition identities, the cofunction identities, the even odd ones, the Pythagoras, Euler's identity is the only exception, and your strategies to prove them. Now what we have to do is work on the right hand side. The right hand side has got a lot more interesting identities. Look at that. Does that scare you? It shouldn't. They're all really easy. I'm going to make them look easy. That's why they pay me. And that's what we got to do next. We want to prove everything on the right hand side, and then we'll dominate this sheet. You'll have it in your heart and in your mind, and it'll feel really, really good to be able to look at these sheets and say, hey, I own every one of these identities. I can prove every single one and know exactly why. Okay, so I guess you understand where we've been. This is what we've proven before, and we reviewed a lot of these, and this is what we got to do now: prove every single one of these on the right hand side. By the way, if you haven't printed this, you should. I'll have it on the internet, on the website soon, or if it's not already on there, make sure you print this and carry it with you. It's the famous identity sheet. I may modify it a little bit just to make it look cleaner, but this is the general gist of it. All right, enough said. Talk is cheap.